Hi, I'm Marv Geller, and I'm president of the Atmospheric Science section. And this is one of the big events for the Atmospheric Science section, our Bjerknes lecture. And I'm very pleased that I have the opportunity to introduce Dr. Joan Alexander. M stands for Joan, okay? And Joan actually came out of planetary atmospheres, and she did her doctoral studies at University of Colorado. But in quite short time, she's established herself as one of the very leading workers in the world on one of the most important subjects in atmospheric science, or middle atmospheric sciences, and that is how to take proper account of gravity waves in modeling of the large-scale flow and transport of chemical constituents. And Joan has really been leading the way, one of those leading the way. Her present position, she's with Colorado Research Associates, and that's a division of Northwest Research Associates. And she's also an affiliate faculty at University of Washington, and also a lecturer at Colorado University. So these are clever places, getting Joan on their side. Anyhow, Joan's talk today will be on gravity wave sources and effects in the middle atmosphere, observational constraints for parameterization and global models. Joan.
So I'm going to talk today about observational constraints for the problem of parameterizing the effects of gravity waves in middle atmosphere models. And although this talk will focus on observations, this is actually, what I'm showing in this slide is actually a model result. And this helps to illustrate some of the important properties of gravity waves, so I'm going to take a moment to describe those. This shows temperature perturbations in the middle atmosphere above a storm, which is modeled here, and this shows the cloud outline in the troposphere. The domain of this model here is about 1,500 kilometers horizontally and about 90 kilometers vertically. So we're seeing these waves propagate from their source in the troposphere all the way up to the mesopods. The color background shows temperature perturbations, and you can see that the waves, even from this single source, have a very broad spectrum of properties. You can see a wide range of horizontal wavelengths in these data, and also you can see the range of intrinsic frequencies, because the intrinsic frequency of a gravity wave is related to the angle that the wave makes, that its lines of constant phase make from the vertical. So the very highest frequency waves are oriented most vertically, and the lower intrinsic frequency waves are oriented more horizontally. Intrinsic frequency also indicates the magnitude of the relative magnitude of the vertical group velocity of these waves. The highest intrinsic frequency waves propagate very quickly from the lower atmosphere to the upper atmosphere in the matter of a couple of hours in some cases, whereas the low intrinsic frequency waves take much longer time to propagate through any given height region in the atmosphere. And you can see that effect here, where the leading edge of the signal, which is an indication of the group velocity, has only propagated partway up in this model, partway into the middle atmosphere at this time. It takes a much longer time for these low-frequency waves to propagate to higher altitudes. You can also see wave breaking, which is occurring here in the mesosphere in this model, and wave breaking leads to mixing effects and transport of trace constituents in the atmosphere. Gravity wave breaking is also associated with changes in the background wind and in driving mean meridional transport circulations. So we don't have nice pictures like this from observations. We wish we did. Instead, what we have, each observation technique tends to pick out sort of a certain kind of gravity wave, a certain scale, or a certain range of vertical wavelengths or frequencies or whatever. And you can only usually see them at a certain height range from each observation. So we have to use models like this to try to take all the observations we have to try to put together what we need, and what we need is a global picture of the occurrence and properties of gravity waves. This schematic is meant to illustrate some of the varied effects of gravity waves in the atmosphere. What's shown here are sources. Flow over topography is an important source. Convection, deep heating inside convection, and shear relative to the temperature perturbations in convection give rise to generate gravity waves which propagate vertically. Their effects are felt in the stratosphere where they contribute to driving the transport circulation. This is a latitude height schematic. So it drives this mean meridional transport circulation in the stratosphere, especially important in the sort of the spring to summer transition season. They are implicated in driving this pole-to-pole circulation at the mesopause, which leads to a reversal of the normal temperature gradient. Temperature is shown as the background color in this figure. The summer mesopause is very cold, just the opposite of what you'd expect from radiative heating considerations, whereas the winter mesopause is much warmer even than the summer. And that's because of the sinking motion and this pole-to-pole transport circulation in the mesosphere. At higher levels, even gravity waves have been implicated in mixing and changes in the homopause. Important chemistry is involved when you change the constituent ratios, and even, in fact, implicated in triggering plasma instabilities in the ionosphere, which can extend to very high altitudes, although there's still debate about those effects. Gravity waves also are known to, or believed to have important effects on other planets and even in the sun. So there have been some important trends in computational performance in global circulation models over time, and in recent decades these increases in computational performance have led us to dramatic increases in resolution in global models, and we're starting now to resolve some of the scales that gravity waves cover. Gravity waves, the important scales, at least for the middle atmosphere, don't go much lower than 10 kilometers, but extend to thousands of kilometers. And so we're starting to resolve some of these larger scale gravity waves in models. However, their vertical wavelengths will change as a function of height if there's any wind shear in the atmosphere. And scales as small as a kilometer, vertical wavelengths as small as a kilometer may be quite important to resolve. So we're really a long way from being able to really model gravity waves in global models. Periods can also be very short. So that's part of the reason there's interest now. Not only do gravity waves have effects at a wide range of altitudes and sort of spanning a lot of disciplines covered by our membership in the AGU, but there's also sort of the next scale of interest in global models right now. So we need observational constraints right now, both for parameterization of the gravity waves that are not resolved, but also to sort of validate the waves that are resolved, since the sources for the waves, for example, convection, that itself is a parameterized process in a global model, and there's no guarantee that the model is going to generate a realistic waves with a parameterized source. So observations need to constrain both the parameterized part of gravity wave effects as well as the resolved waves in these models. So there are three sort of important components to parameterizing gravity waves. First, you need to know what the sources are, and we're still struggling with really understanding these sources, which ones are important relative to the others, what their nature is, and most importantly, what's the momentum flux spectrum that each source generates under a certain set of conditions. And so this is the second part. And the third part would be how to describe the dissipation of the waves that are generated as a function of height. And that gives you some important forcing terms in a global model. But this piece of the problem right here, and relating this to sources, this is a major source of uncertainty in models right now. It's in fact the biggest problem, the thing that I'm going to focus on in the talk and is sort of the focus of most of my research, that is trying to observe or trying to infer from observations, because we don't really measure usually momentum flux. We have to infer it sort of indirectly from the observations that we have. And we need to try to relate that to sources so that we can get a more accurate parameterization of these processes in global models. Just to sort of underscore this problem, I've collected results from two papers that came out in 1998, both of them. On the left-hand side is one, and on the right-hand side is the other. In the top panel of each is a sort of a control simulation where an isotropic source of gravity waves was input near the tropopause. It's the second panel. Each panel shows an experiment where they change the sources in some way to try to make the background winds, which are shown in these panels. These are zonal mean winds as a function of latitude and height in the atmosphere. So they tweak the sources to try to get a good zonal mean state, and then compare that to the observations, which are shown in the bottom panel of this slide, bottom panels. And the thing, though, is that in order to get the experiment to look like the observations, comparing the second and third panels on each side, this model, this study by Manzini and McFarlane, they reduced the amount of westward propagating waves, the momentum flux carried by the westward propagating waves. They had an excess of that, excuse me, I'm not sure what I said, in crossing the tropopause. On the right-hand side, they needed to reduce the amount of westward momentum flux. So opposite changes to the gravity wave source spectrum were inferred by trying to use a GCM to invert this problem and infer what the sources look like. So what this tells me, I mean, I don't really understand these results yet. We don't necessarily have all the information we need to try to understand these right now. But it does tell you that it's dangerous to try to do that. You need to explore a very broad parameter space for the sources, because the answers you get are not necessarily unique. And you just can't do that in a GCM study because they're too costly and time-consuming to run. So what we need from observations are measures of the momentum flux spectrum versus phase speed. If we could get that, that would be most ideal. We also need to have some idea of the horizontal wavelengths associated with the waves in this spectrum. And we need to relate the spectrum to source properties. How does the spectrum vary for a given source and under what conditions in the background atmosphere? And finally, we need global coverage. Or in lieu of that, we need a detailed understanding of how to relate the spectrum to the source so that we can describe it accurately in a model and extrapolate globally. This is a difficult challenge. We have some exciting new observation techniques out there. The top panel shows the results from Spirit 3 radiometer, I believe it is, from MSX satellite. These are infrared radiometer measurements looking below the limb. And when they look most nearly along the line of constant phase, if you remember back to the very first panel I showed, they see large temperature perturbations in the stratosphere. And this is an imaging instrument, so you can think of this as sort of an X and Y map of temperature perturbations at a certain level in the stratosphere. And they see these sort of circular ring-shaped patterns in these data, which are very reminiscent of things we see in models. This is a three-dimensional model of a storm. This is looking down on the storm. Near the surface, these are the contours of the strongest updrafts in the center of the storm. And the shading here shows the contours of vertical velocity in the stratosphere above the storm. So this is a sort of similar view to what we're seeing here, same sort of concentric ring-shaped patterns in the phase fronts. And in fact, there was a very deep convective source near the center of this pattern in these data. And so it's really the first observational verification of waves generated by convection in the seen in the stratosphere above a storm by satellite. But those data only span a matter of weeks, I guess 10 weeks total, and they're fairly limited in their coverage. We hope to launch instruments like that, improvements on them in the future, on future satellites. I'm going to focus on satellite observations because of their global coverage. I'll also discuss the results of a new radiosonde project initiated by the SPARC program, part of the WMO. And that's because we really need to get a handle on the global coverage of these. So the microwave limb sounder is an instrument on the UR satellite, and it was used to infer gravity wave activity globally. And on the right-hand side, I've listed some important properties, the vertical wavelengths of the waves that can be observed in each of these techniques. And I'll show you why that's important. But in this technique, you really only see the very longest vertical wavelengths in these measurements. I'm also going to show results using GPS and radiosondes. GPS is the radio signal from the GPS constellation is picked up by a low Earth orbiting satellite and used to infer temperature profiles in the stratosphere. And from that you can infer short vertical wavelength waves. And then there's also these infrared limb sounders which have been used to infer temperature profiles. LIMS is a satellite from the past, and Krista is a new instrument that's flown on the space shuttle a couple of times. And we have a couple of weeks of very intensive global coverage with this technique. And this technique can observe some of both the short vertical wavelength waves and the long vertical wavelength waves, sort of halfway straddling the two other sets. The reason vertical wavelength is important is because it will change as a function of height when there are changes in the background wind as a function of height. So, and we use linear theory. I'm going to show a result from linear theory to try to give some insight into this. This is the intrinsic frequency, and it will vary as a function of height. This would be constant if the horizontal properties of the atmosphere are horizontally homogeneous. And, but if there's variations in the wind as a function of height, then this will change as a function of height. And that's also related to the vertical wave number, which is 2 pi over the vertical wavelength, and related to the buoyancy frequency, which is a measure of stability. So the vertical wavelength, if you solve for that, is directly proportional to the intrinsic phase speed, at least in this simplified approximation that I've shown here, and was also proportional to, or inversely proportional to, the buoyancy frequency. So if we have changes in the background wind, this intrinsic frequency changes linearly with that. And so as the intrinsic phase speed increases, you get an increase in the vertical wavelength. As it decreases, you get a decrease. And these bottom panels show a result from Sato and Yamada's paper where they were examining a gravity wave approaching a critical level. This curve right here shows the background wind in the direction of propagation of the wave, and this wave's phase speed was approximately 0. So as you go from 15 to 20 kilometers, this wave is approaching a critical level. That's where its phase speed equals the mean wind speed. And you can see its vertical wavelength going from something much longer to something very short. So, and they were actually able to describe this profile as mainly due to a single monochromatic wave. Now the microwave limb sounder satellite observations shown here in the top panel measured gravity wave activity and binned them globally, averaged over a 2-month period here. You can see the color shows the gravity wave activity with the red to white here showing the largest values. And initially, in this initial paper, it was described as showing patterns in, or described as illustrating where gravity wave sources were globally. And it was mentioned that this was likely related to jet stream instability, because the largest values of the activity here occur in the winter jet stream in the stratosphere. This is at 38 kilometers. And there are also a lot of activity in the summer hemisphere and sort of the subtropics. And we have a lot of deep active convection in this region. So it was believed that this was showing regions of active convection. However, if you just take uniform gravity wave sources globally and let them propagate through the observed background winds, in fact, you see very similar patterns. So this is with no source variations. And the reason is that here where the winds are very strong, the vertical wavelengths of the waves have grown large. And those are the only ones that this observation technique can see. And I've illustrated that in this panel. It shows here the function of height and phase speed or background wind. This is a zonal wind profile. So the waves propagating opposite to the direction of the shear are in a situation where their vertical wavelengths are increasing as they propagate vertically. These waves with phase speeds in the direction of the shear, they have decreasing vertical wavelengths. These would be invisible to this satellite. These would stand out prominently in these data. And in fact, the bigger the background wind change from low altitudes to the observation level, the larger the wave activity that is observed. So it's somewhat of an observational artifact that these patterns match up, or that these patterns appeared in these data. But there is a lot of important information in these data. One just has to keep this effect in mind. These are results from the global positioning satellite that I mentioned. These are published in a paper by Suda and colleagues just this year. And this shows a global map of temperature perturbations, short vertical wavelength temperature perturbations in the stratosphere between 20 and 30 kilometers altitude for the November-February season. And on the bottom panel, we're seeing black-body temperature. This where these very low values occur here in the tropics and here as well are indications of where there's strong, deep active convection averaged over this month period here in this panel. And you can see that some of the largest gravity wave activity values occur here directly over the deepest, coldest clouds in the atmosphere. So these data do obviously show us some information about sources. Superimposed on this is a latitudinal trend, where we see the largest values in the tropics and the lowest values at higher latitudes. So what does this mean? Does this mean that there's more gravity wave momentum flux in the tropics than at high latitudes? Well, the microwave limb sounder showed us quite the opposite for the same time period, same winter period. It showed us largest values in the winter hemisphere. And I believe, in fact, that this is related to the different kinds of waves that one can observe as a function of latitude, and also related to the fact that this technique observes short vertical wavelength waves, whereas the MLS observes long. You also see a similar low latitude enhancement if you look at the CRISTA data when you filter for some of the shorter vertical wavelengths they can resolve. And looking in the very lowermost stratosphere, you also see a trend for the largest wave activity to occur near the equator. This tends to go away as you go up higher in altitude in these data. This data can go up quite high into the mesosphere. But also, there is clear indication of sources. I'll show some results later. I studied by Steve Eckerman and Peter Prissa analyzing observations here over the southern tip of South America, where obviously we're seeing mountain waves generated by flow over the southern Andes. Then I wanted to show some results from the SPARC radiosonde network effort, where radiosondes have been collected all over. Radiosonde temperature profiles have been collected at high resolution from these red dot sites all over the world. These are unpublished results so far, but collected as a function of latitude, these also show a peak at low latitudes in the potential energy in each season, both the May, August, and November, February season shown here. So the nature of this peak at low latitudes is what I'd like to briefly describe an explanation for. This is a summary of some of those previous observations. And this is GPS filtered at two different wavelength bands. This is keeping only waves shorter than 10 kilometers. This is keeping only waves shorter than 5 kilometers. And here are some radiosonde results from the Australian radiosonde network anyway. These all show this prominent peak at low latitudes. And this peak is, one thought is perhaps it's due to trapped planetary waves in the atmosphere, perhaps Kelvin wave activity. But the peak is much broader in latitude than one would expect if it was only due to trapped equatorial waves. So the explanation that I'm proposing for this is that the peak is actually related to the variation in the Coriolis parameter as a function of latitude. It's got its lowest values right at the equator and high values at higher latitudes. This Coriolis parameter, which I've called F here, this defines the lowest intrinsic frequency that a gravity wave can have and still propagate as a gravity wave. So what I've plotted here in the lower panel is as a function of latitude, I've plotted the longest period that a gravity wave can have. And this shows a definite peak for where periods can be as long as several days, up to maybe 5 days or so, when you get closer to the equator. Right at the equator, this number would go to infinity, of course. So the fact that this peak occurs in the longest period as a function of latitude has implications for the amount of gravity wave activity that you would observe as a function of latitude if your technique can see these low-frequency waves. So this is a spectrum, this is a schematic, really, of what the spectrum of kinetic or potential energy tends to look like from observations. If you, we can't really measure intrinsic frequency, which is what we would really like to know, but it's ground-based frequency is observed, and this is always sort of a reddened spectrum, always where the largest values in the energy spectrum occur at the lowest frequencies. And so if this spectrum that's observed also is representative of the spectrum of intrinsic frequencies, then as you get closer to the equator, this is running out. I wondered if that other laser plotter is available, or laser pointer is available. As you get closer to the equator, you can integrate over the entire spectrum of waves of gravity waves, which ranges from the Coriolis frequency to the buoyancy frequency. And that area under these curves gets larger and larger as you get closer to the equator. Thank you. Okay. So you'd expect, if this is in fact what the intrinsic frequency spectrum looks like, that as you look closer to the equator, you'd see larger energy in some sort of average sense. This is only part of the picture because, in fact, these low intrinsic frequency waves have the slowest vertical group velocities. Slow vertical group velocity waves stay close to their sources in the lower stratosphere. They're going to hang out there for a much longer period of time than a high intrinsic frequency gravity wave, which is going to tend to have a fast group velocity, and once generated will propagate very quickly to higher altitudes out of your range of vision, essentially. And so if there's intermittency in the way waves are forced, if they're forced only intermittency, such as we expect in convection, for example, where the convection's active and then it's not, then if you average over a month of observations, the low frequency waves are going to dominate your signal because they're there more often because they propagate so slowly away from the source. So I've translated that into probability of observation. And that's what's plotted here on the left-hand axis as a function of intrinsic frequency. And so the probability dramatically increases as you move to lower intrinsic frequencies because of this slow group velocity effect. And as you get closer to the equator, this minimum frequency, which is the Coriolis parameter, gets smaller and smaller. And if all other things are equal, which to make this plot I had to assume, then you'd expect a much higher probability over a much wider range of intrinsic frequencies, higher probability of observing waves as you get closer to the equator compared to low latitudes. So what this means that if forcing is intermittent, you don't need a terribly reddened spectrum in intrinsic frequency to get a peak at low latitudes. Fairly shallowly sloped spectrum as a function of intrinsic frequency, and I'm referring again to this figure, doesn't have to be as steep because these low frequency waves just hang around near the sources so much longer. So I conclude from this that the presence at low latitudes of low frequency waves that are excluded from the higher latitudes will lead naturally to a peak in observed gravity wave activity near the equator. This, I think, is part of the reason, part of the explanation for some observations published from a global circulation model study done at very high resolution. This is from Karusato's work. And this is a global aqua planet model. And so all the sources, or the main source, is convection, for sure. And what she's shown here is a plot of intrinsic frequency as a function of latitude. And the color shows, let's just look at this right-hand panel only, shows the potential energy or the temperature, the power in the temperature spectrum as a function of frequency and latitude. And these solid lines here plot the Coriolis frequency as a function of latitude. And you can see that a lot of her power in her spectrum is piled up right against the intrinsic frequency, just as would be predicted by the group velocity effect. And also that the range of intrinsic frequencies is much larger at high power at the low latitudes and much narrower at the higher latitudes. So I think this is kind of an explanation for the shape of this power spectrum observed in this model. Another effect that influences observations of variations in gravity waves globally is one described by Steve Eckermann in a paper he wrote in 1995. There's commonly observed an annual cycle in gravity wave activity at high latitudes in the stratosphere, where there's a pronounced maximum in the wintertime and much lower values in summertime. Well, just using arguments from linear theory, we expect that gravity wave amplitudes will grow as a function of height as the wave propagates vertically. And this growth in the square of the amplitude of the perturbation is inversely proportional to the density. Now, in the cold winter stratosphere, the change in density as a function of height is much steeper. So they have much lower densities at given geometric height in the atmosphere. And so you would expect, if there is no substantial dissipation differences summer to winter, that the average energy observed, like averaged over, say, a month, would be much larger in the winter months than in the summer. And the reason for Steve's idea, really the motivation for Steve's idea, was an analysis of rocket sounding data. We're shown here for two stations at 55 north and 75 north, which show this pronounced seasonal cycle in gravity wave activity at two different levels. This is just at one level in the stratosphere. And the solid line shows this simple model result and how it would vary seasonally. You can see that certainly in the upper stratosphere, this could potentially explain a large amount of the seasonal variation in these data. It should also have effect in the lower stratosphere, but it should be weaker. Now, when I give talks like this, my colleagues sometimes get upset with me. People who make and analyze observations, they say, it sounds like you're saying observations don't tell us anything about gravity waves. And that's not what I want to say. I personally believe observations are key, and I think at the beginning of my talk, I hope I stressed that models desperately need guidance, and we need these to come in the form of constraints from observations. But I think what I do want to say is that you can't just take one set of observations that's observing just some limited portion of the gravity wave spectrum. It can't, no observation technique can see the whole big picture on this broad spectrum of gravity waves that's likely present in the middle atmosphere. Instead, we have to use models and observations in concert. The models help put any given set of observations in context and help us understand what part of the problem each observation technique can help tell us about. So now I'm going to describe some studies that actually dig deeper into some of these data sets and tell us more specifically about the nature of gravity wave sources and the spectrum of waves that might be generated from those sources. This is a paper by Charles McClandress that I was also a co-author on, where we looked at the microwave limb sounder data again in greater detail. The top two panels show temperature variance observed by the satellite at from 10 to 50 degrees latitude in the northern hemisphere and the southern hemisphere for the summer seasons in each hemisphere. And as I described earlier, the latitudinal variation in this temperature variance has a lot more to do with the background winds in the stratosphere and much less to do with gravity wave sources. So the fact that we see very low values here and higher values at this latitude is not very telling. However, the longitudinal variations are not predicted by the background wind effect. These are the background winds at the same height, the wind speeds, and you can see they're very nearly constant in longitude, very little variation. These variations are instead very telling of variations in sources at this latitude. So if you restrict yourself to looking at the latitudes where we have a clear signal, in fact, in this paper, we described the fact that we think that outside of these main latitude bands where there is a signal, any gravity wave signal is lost in the noise. We're probably just seeing noise. But if you restrict yourself to where we do have a strong signal and then plot gravity wave activity as a function of longitude, that's these two panels for the same northern hemisphere and southern hemisphere observations in the summertime, you can see that the variations with longitude are very highly correlated with variations in outgoing long-wave radiation. And this, again, is an indication of the occurrence of deep convection in the troposphere. And this is an inverted scale, so the lowest values are associated with the deepest, highest clouds. And these are very tightly correlated. And I believe that this is an indication, a very clear indication of deep convection generating long vertical wavelength waves. Those are the ones that the satellite can observe. And that's actually an observational verification, I feel, of one of the mechanisms for how convection generates waves. There are several sort of out there that are still being debated, which is most important. Well, this observation seems to validate this deep heating mechanism, which is one that was described by Murray Salby and Rolando Garcia in a paper where they were really focusing on more planetary scale motions, but the idea is the same. That is where you have a heat source, latent heating inside a storm in the troposphere. This projects most strongly onto a wave with a vertical wavelength twice the depth of the heating. However, because the buoyancy frequency changes by a factor of 2 as you go from the troposphere to the stratosphere, this simple relationship from linear theory about the gravity wave relationship between vertical wavelength, intrinsic phase speed, and buoyancy frequency, as I mentioned before, tells us that the vertical wavelength should drop by a half when you go from the troposphere to the stratosphere, so that the vertical wavelength predicted by this deep heating mechanism is expected to be the same as the depth of the heat source. And it seems to be a very clear indication in the previous slide that it's only where we have the deepest convection where we see the very strongest signals in the MLS, which can only observe the longest vertical wavelength waves. Well, this vertical wavelength is also related to intrinsic frequency. So this predicts peaks in phase speed. If we know the depth of the heat source, we can predict where these peaks in phase speed for the momentum flux spectrum would occur. However, these data do not give us a measure of the magnitude of this peak, and that's a shortcoming. So we have to use models and other observations. We do have aircraft observations that do help constrain the magnitude of the momentum flux for gravity waves over deep convection, though there's still a number of uncertainties in those data as well, and I'm not going to show any results from that. Now I'm going to show some results from radiosonde observations at a tropical site, 12 degrees south in the Indian Ocean, far from any topographic sources. These are radiosondes where in the lower stratosphere, 18 to 25 kilometers, temperature perturbations are collected and also wind perturbations. And you can actually derive estimates of the momentum flux in this 18 to 25 kilometer range in the atmosphere as a function of time. And these radiosondes span 6 years. We had 6 years of data to work with in this study. And we see some very pronounced annual and interannual variations in these fluxes, and the interannual variations seem very closely tied to the variations in the stratospheric winds associated with the quasi-biennial oscillation in the tropical lower stratosphere. And you can see that in the background wind observations from these same radiosondes here showing every other year westward and eastward winds. Well, in a corresponding model study, I examined various sources that could give a reproduction of those time series in the momentum flux that were observed. And the results of this study suggested that what we're seeing are convectively generated waves, but the waves in the radiosonde observations are quite different from those observed in the microwave limb sounder. They're very low intrinsic frequencies, where we were seeing high intrinsic frequencies in the microwave limb sounder. And in these data, these low intrinsic frequency waves suggested that the source was again convection, deep convection, where the source was up high in the troposphere near the tropopause, but a different mechanism, where you have a wind blowing sort of over the top of this potential temperature surface perturbation caused by the heating in the storm, and that wind generates waves much as flow over mountains generates waves. This mechanism predicts a very different signature in the momentum flux spectrum. It would predict a peak in flux at a phase speed equal to the storm speed. And that's quite different. The other mechanism predicted intrinsic phase speeds peaking relative to the depth of the heat source. So I think we have a weaker but also observational confirmation of a very different mechanism that may be the most important one for these very low frequency waves. We're really still not sure, but it does indicate that there's more than one way to think about how convection generates waves, gravity waves. These radiosonde results that I mentioned, again, this is Bob Vincent's plot from work that is not yet published, also give us important information about the direction of propagation of the waves. And in this tropical region around Indonesia and New Guinea, there's a definite preference for eastward propagating waves in these data. And these is anisotropies, as I showed in that very early plot, comparing the two global circulation model experiments, is an important parameter that we need to get a handle on for global circulation modeling. From microwave limb sounder at high latitudes in the extratropics, this shows the southern hemisphere, 20 south to 80 south, in winter time, June, July, August. And again, the latitudinal variation has much more to do with the variation in the background winds, shown here in this plot for the same latitudes and longitudes. So that doesn't really tell us that much. However, the longitudinal variations shown here show a pronounced peak here just in the lee of the southern Andes, and this shows the topography there. So this is an apparent correlation between gravity wave activity and mountain-generated waves, where we expect them to occur. These are results from the CRISTA experiment. It's from a paper published by Steve Eckerman and Peter Prusa late last year. This is an experiment flown on the space shuttle, and it's an infrared limb sounder, as I mentioned earlier. And they have three different telescopes looking at three different views, 1, 2, and 3 here. And this shows the temperature profiles for each of those three views. And so you clearly see the vertical wavelength signature in a wave observed here, again, over the southern Andes. And in fact, the change in the phase as a function of position, and also an expectation that the phase speed is going to be 0 or close to it for mountain-generated waves, allowed them to infer also the horizontal wavelength for the wave. And given all this information, they're actually able to calculate the momentum flux carried by this wave. And they were even able to infer from the background wind profile from other sources, from global data, that this wave is probably approaching its critical level as it propagates in height. And so here at above 30 kilometers or so, its vertical wavelength shrinks below the resolution, and probably that wave dissipated in this region. So this is the first really observational verification of mountain waves in the stratosphere from a space-based platform. And observations like these in the future will likely tell us a great deal about sources for waves globally. In fact, in additional work with using models to help infer what the observations are telling them, they're in fact getting information about global distribution of gravity wave sources from flow over topography. So, let's see. 7 minutes? Okay. So I think I probably won't describe much of these results, but I'm also doing some studies of using estimates of the zonal mean gravity wave forcing. So these are the effects that we expect gravity waves to be having in the stratosphere. These are inferred from global data. I'm working with Karen Rosenloff. She has been refining this technique since her thesis work at the University of Washington several years ago. And what is done is you can estimate the total forcing, total wave-driven force that must be present in the atmosphere in order to explain the zonal mean transport circulation in the stratosphere. And you can subtract what we know is the wave driving from the resolved waves in the global data sets. So this is the resolved Eliason-Palm flux divergence. Subtracting those two gives you some residual. And if we treat this residual as being due to gravity wave dissipation, we can infer some things about the global distribution of gravity wave sources. Now this kind of work suffers the same limitations as the GCM studies I showed at the beginning. However, because we're using simple models instead of GCMs, we can explore a very broad range of the source parameters for the kinds of waves we're putting in at the bottom, and we can see what parts of that parameter space fit the observations, what parts don't, and at least be able to say whether this does constrain the sources or does not. So I think I'm not going to show many of these results, but that's just some additional work we're doing. I'm going to leave time for questions. Instead, I'm just going to summarize some of the global constraints that we do have on gravity wave spectrum in the lower stratosphere for input to global circulation models. There do appear to be some important latitudinal variations. Comparing the tropics and the extratropics, there are indications that, and I haven't covered many of these in this talk, so I'm just summarizing here of what we think we know. There's indication that there are some much higher phase speed waves present in the tropics that are not very prominent in the extratropics. These phase speeds tend to be clustered closer towards 0 or smaller values. And this goes with our intuition about what we'd expect given differences in sources, where deep convection is an important source for gravity waves in the tropics, whereas flow over topography, shallower convection because of the shallower troposphere, and frontal systems are more likely important sources in the extratropics. Also, the tropics likely include some of these very low intrinsic frequency waves that are simply excluded from higher latitudes because of the variation in the Coriolis parameter. Now we have some other constraints which are not quite so well substantiated, and that's why they all have question marks after them. But in the tropics, we have some indication that the sources are more intermittent than they are in the extratropics. And this also would go with the idea that deep convection is a more important source in the tropics than it is in the extratropics. We also have some indication from a couple of sources, a couple of studies, that the average momentum fluxes crossing the tropopause in the tropics may be smaller than those in the extratropics. But we still have some conflicting evidence on this, so this is by no means a settled issue. We have also some evidence that the wavelengths on average that are important to driving the atmosphere in the tropics have somewhat longer values, and that somewhat shorter horizontal wavelengths play a more prominent role in the extratropics. There are also important issues about anisotropies, variations in the propagation directions of the wave, and the weighting of the momentum flux spectrum is a function of propagation direction, but these are not really well sorted out at this time when you're trying to discuss the entire spectrum of gravity waves. And we also expect, given these sources, that there should be important seasonal variations in the forcing of gravity waves, and yet from the observations I don't feel we really have much to stand on in order to say what those variations are. So that's, I'll just stop there. Take questions.